Last time we talked about the effectiveness NTU method. So the effectiveness NTU method, and I believe you had to solve a problem for the homework today using the effectiveness NTU method. Let me just say that you can usually find in a textbook, this is not in our textbook, but I don't have a digital copy of our textbook, but there's a table in other heat transfer textbooks as well, where you'll have a whole host of relationships or equations for the effectiveness as a function of NTU and C sub R, which is the ratio of minimum to maximum heat capacity rates for different flow configurations. Counterflow, this is the one we developed last time, didn't we? Spent 3 pages developing that equation for concentric tube counterflow heat exchangers. This is the equation that we derived. And it's not a trivial equation to derive, but it was completely derived analytically. You had homework today, and in this textbook that we have for this class, it doesn't give this equation. It asked you in the homework to derive it, basically. And so when C sub R is equal to 1, then there's a limit problem here. And whose rule do you have to use? Either you say the person's name is La Hopital or La Hospital. La Hopital. Yeah, that's the way I learned it too, but it looks like La Hospital. And so hopefully that was, you were able to do that successfully. But these equations, this one converges to that one when C sub R is equal to 1. What's always interesting is this result right here, probably one of the most used lines in the table. What does it say? It says for all heat exchangers, when C sub R is equal to 0, use this equation. All right, well that equation looks a lot easier to use than this one or this one or this one or this one, right? But what does it mean when C sub R is equal to 0? Well, what was C sub R again? Let me jump back to a clear page. C sub R was the minimum heat capacity rate divided by the maximum heat capacity rate. So the heat capacity rates were the product of mass flow rate specific heat. How can I get C sub R equal to 0? So C sub R equals to 0, you can think of 2 cases. C min equal to 0, or play with not C max, make it C max do what? Well, no, not 0, but go off to infinity, right? Let's say C max is much, much larger than C min. Think about this one. How would I ever get C min to be 0? Well, C min is equal to the minimum of the mass flow rate times specific heat. Whichever fluid stream has the lower product of mass flow rate specific heat. Well, maybe I could have specific heat of the fluid go to 0 for one of the fluid streams. Not realistic. How about the mass flow rate of one of the fluid streams go to 0? Not much of a heat exchanger, is it? It's like the fluid's going to be stagnant. You're not going to bring any fluid in and out of that one side, the cold side or the hot side. So this really is the way you get C sub R equal to 0 is you get C sub max much, much greater than C min. All right. So how do you get C sub max much, much greater than C min? When do you observe that for any heat exchangers? Let's think of C max as being the hot fluid and C min being the cold fluid. Okay, that helps put meat on the bones, or make it more tangible, the discussion. So the mass flow rate of the hot fluid times specific heat of the hot fluid much, much greater than the mass flow rate of the cold fluid, specific heat of the cold fluid. And we said we're not going to let mass flow rate of the cold fluid go to 0. That doesn't make sense. We're still going to have some mass flow rate of the cold fluid. So I know that you basically have a very large mass flow rate of the hot fluid, or you get a very large specific heat. Are there any areas or thing that you can remember in heat transfer thermodynamics where the specific heat sort of went to infinity for a fluid? Condensation, phase change. Okay, let's talk about C sub P. What is C sub P defined as? From Thermo 1, just the rate of change of H with respect to T holding pressure constant. So what you do is you play this game where you start with 1 pound or 1 kilogram chunk of fluid that's in the liquid state. And you think about this. You're saying, I'm going to plot H as a function of temperature, and I'm going to start that 1 chunk of fluid, 1 pound, 1 kilogram of fluid at a low temperature when it's in the liquid state. And here it is, it's 20 degrees C, and it's got a value of H. There it is. It's a low value of H. As I start to add heat to that liquid water, and I bring in some Q, what's going to happen to the enthalpy? It's going to go up. What's happened to the temperature? It's going to go up, true? So we're going to go up, up, up. Let's do this for 1 atm pressure. So it goes up to 40 degrees C, 60 degrees C, 80 degrees C, and then at 1 atmosphere pressure, something very special happens. It gets up to 100 degrees C for that water. It went up. There's the enthalpy now. It went up. Now as I bring in more heat, does the temperature continue up on a straight line or close enough to a straight line? Or what happens to the enthalpy as I bring in more heat? Is sort of the temperature stalls and enthalpy keeps going up. And so it goes up, 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 till it goes from H of F to H of G. Now what about that 1 pound or 1 kilogram of water? If I bring in more heat, the H is going to go up, and the temperature is going to start going up again as well. But this time, it's all vapor. And I have the specific heat, the slope of that line of the vapor. The slope of this line is the specific heat of the liquid. True? So you say, oh, what is the slope of the line when it was just doing that? Changing phase at constant pressure without changing temperature. It's just going from such. What was the effective specific heat? Infinity. The slope is infinity. So it's like a huge specific heat. And that you realize that ratio C sub R is very, very large or goes to infinity when you have phase change. All right. So this line down here at the bottom of many, many textbooks where they're describing the effectiveness NTU method is used all the time when you have either condensation or evaporation or boiling. We're going to use this today, tuck it away, because it won't be until near the end of the lecture that I'll pull that equation back out and use it. Okay? All right. Well, we have to get the overall heat transfer coefficient. And this is that symbol U. And what are the units, both SI units for the overall heat transfer coefficient, watts per meter squared degree C, as well as in the USCS, something like BTU per hour. That would be a good comparison to watt. Foot squared compared to meter squared. Degree F compared to degree C. Wouldn't that be great units? All right. So how do I calculate this overall heat transfer coefficient? Well, the heat is flowing from a hot fluid to a cold fluid, and there's a wall, some material, typically a tube, the wall of the tube, separates the two fluid streams. So you can think about, in general, some wall Some, it could be round, it could be different shapes, but it's some material separating them. And for simplicity, I just show it as a wall right here. And we have some thickness, typically L or K or T for thickness, because they're often very thin, walled. And we have some thermal conductivity, right? And we have some fluid over here, and we have a resistance to get into the solid, through the solid, out of the solid into the fluid stream. And so we think of these resistors. What do we have? 1 over H. Let's say this is the inside, this is the outside. You could say this is the hot side, this is the cold side, some designation. Let's call it inside times the area inside. That's the resistance for that resistor. We have an L over Ka, or a thickness divided by Ka, for the resistance through the conduction of the wall. And then we're going to have 1 over H on the outside, area on the outside for that. Why do we have different areas? Because you could have slightly different areas. If I'm doing a tube and I have inner radius R1, outer radius R2, then I wouldn't use T over Ka, would I? That resistance for this case through the wall would be the natural log of R2 over R1 divided by 2 pi KL. L is the length in the third dimension, L, right? So often we have heat transfer through the walls of tubes in heat exchangers. All right. So what we do is we replace these 3 resistors that are in series with a single equivalent resistor, and that single equivalent resistor is the 1 over UA. So it's the 1 over HA for the inside. I'm going to just put resistance through the wall because you could use this equation or that equation, and then 1 over HA on the outside. This brings up a point. Which area are we going to use with the U? Well, it's your pick as an analyst. You can pick that if the area inside is used here, then it's the overall heat transfer coefficient based on the inside area. But you could also say that's equal to the same of 1 over U outside, area outside. The numeric value of the U overall heat transfer coefficient, U, might be different if the area is inside and outside is a little different. For example, here, what's the area on the inside? It's 2 pi R1L, and the area on the outside is 2 pi R2L, depending how thick the wall is. How big is the difference between R1 and R2? So when you specify the overall heat transfer coefficient, a lot of times that area you may have to struggle with exactly which area does it match with. Okay. Well, now we're going to take a look at the values of convection resistances and a little review. We have convection heat transfer coefficients. If you have air at its natural convection, it has very low. Isn't that low convection heat transfer coefficients? If you blow the air, it's higher. And then it continues to march up in magnitude. If you have water just sitting there with some slight motion due to natural convection, it's a pretty good convection compared to still air or natural convection in air, but it's not good compared to water if you're forcing it. Look how much of a difference. So you start really pushing that water through the pipes or across surfaces. So the water force convection coefficient is a lot higher. Here's something with oil. Oil is a forced convection, but it's not as good a thermal conductivity of the oil, hence a lower H of the oil. Then you have water that's boiling and water that's condensing. Look at the magnitude of those H's. They're very high. Very large convection coefficients for boiling and condensation. Well, looking back when you took the class heat transfer, you basically found that it was very much dependent on correlations. Convection heat transfer is all about correlations, and they put it into dimensionless parameters. And so when you were solving a problem and you anticipated free convection or natural convection, convection motivated by having buoyancy forces induced by temperature-dependent density in a gravitational field, hot air, less dense, buoys up, cold air, more dense, sinks, hot air rises, cold air sinks. You get motion that way. When in a room there's a hot wall and a cold wall, you get natural convection currents in a lot of places. You expect it to find the very abstract when you first look at it, saying, what? We're looking for a Nusselt number as a function of a Grashof Prandtl to a power. Or the Nusselt number is a constant times a Rayleigh number to a power. Right away I've got Grashof number, I got Nusselt number, I got Prandtl number, I got Rayleigh number. Your head's spinning. Right? And then if I had forced convection, it's being forced through the tube or over the plate. It's the Nusselt a function of the Reynolds, typically to a power, Prandtl to a power. This is not the only form. It's like the simplest form of a lot of these convection correlations. So here it is. This is the game. PR, that's the Prandtl number. I said it out loud. That would be the name. That's the name of that parameter. If I then said, oops, I'm not going to tell you the name, can you remember what the name of PR is? And then I'd say, what is the definition? Just like you say thermal diffusivity is K divided by rho C. So if I know K and rho C, I get thermal diffusivity. We did that last time. That's another property of interest. So this property of interest called the Prandtl number. What is it defined as? From memory. No idea, Professor. I know it's been 2 weeks or more since you took the heat transfer class, right? It wasn't even 2 weeks, Professor. I walked out of the heat transfer final and I was liberated. So what do we recall? Anybody? Time to show off, right? Prandtl number. And then not only what is it defined as, but what does it mean? Give me a description of it. Not just the name, what is the equation, but then what does it mean? How does it help? Why is it being used? What does it describe? So we slowly uncover, it's the Prandtl number, and what is it defined as? Can you see that? Nu over alpha. What was nu? A certain viscosity. I can't remember. Absolute or kinematic? Kinematic viscosity. And then alpha? Thermal diffusivity. Do they have the same units? They actually do have the same units. And so Prandtl is not a dimensional parameter. It's a dimensionless parameter. Now the hard part. Why are we even talking about it? What does it help us dictate? Somebody says, oh, I have a high Prandtl number fluid. I have a low Prandtl number fluid. I have a Prandtl number fluid about 1. What does it mean? Well, there's a couple ways, but basically it's a ratio of the molecular momentum and thermal diffusivities. That's just kind of repeating, oh, it's nu over alpha, momentum diffusivity based like viscosity, or thermal diffusivity. But if you think about it, it's the rate how the thermal boundary layer grows compared to the velocity boundary layer grows. How does the transfer of heat through a flowing fluid compare to the transfer of momentum through the flowing fluid? All right? And it's not a one-to-one, but in general, the boundary layer thickness is proportional to something like the kinematic viscosity times some time square rooted. And so if I take the Prandtl number and here, I'll do it this way. I'll take the thermal, the boundary layer thickness, the momentum boundary layer thickness, and I'll divide it by the thermal boundary layer thickness, and then I'll square that quantity, okay? That would be like taking the square root of nu t, dividing it by the square root of alpha t, all right? Squaring them gets rid of the square roots and cancels the time, and I get nu over alpha. I get the Prandtl number. The Prandtl number is a measure of how fast the velocity or momentum boundary layer grows compared to the thermal boundary layer. I know there's a factor of 2 in there. Okay, so if you want, you take the square root of the Prandtl number, but forget the square root. All right, that was great. How many people remember seeing and hearing about the Prandtl number before? That's exactly right. Did you know that probably on this slide right here, one question will be on the mechanical engineering FE exam? I would say one question. How many people have taken the FE exam? Nobody? How many people plan to take it? Yeah, I'm going to help you right now. Seriously. The probability is over 50% that one question on the FE exam will come from this slide right here. One way, shape, or form. They'll say, what is the Prandtl number a ratio of? And they'll give you a list of 4 or 5, and you got to pick one. That's it. They're going to say the same thing either for the Nusselt number, or what's the one down here? Reynolds number or the Grashof number. They'll do it. All right. So let's do this discovery. What is it? By name, it's the Nusselt number. By equation, what is it? Very good. That's pretty good. And now, HL over K, or whatever the length scale is, it could be a diameter for the length scale, it would be HD over K. Okay. Now, what does it mean? It took me a long time to try to convince you of anything of the meaning of Prandtl number, and it's probably going to be a lot harder for the Nusselt number, but it's a pretty abstract concept. Here's some definitions of it. It's a ratio of convective to conductive heat transfer. I've seen that a lot. It's kind of like, look at H over K. Convective to conductive, done. Dimensionless heat transfer coefficient. I normalized H. That's really what you've done. So when you have a high Nusselt number, it indicates that somehow for a fluid layer that you're transferring heat through, okay, if you have a high Nusselt number, then it's like the advection is adding a lot to the transfer of heat compared to if it just been stagnant in conduction only. There you go. All right. Reynolds number, your old friend, true? So that's the Reynolds number. What's it defined as? Rho V L over mu or V L over nu. True? And then you say to yourself, what is it physically? What is the good description of it? It's a ratio of inertia to viscous forces, or somebody say it's dimensionless flow velocity. That's not as common of a definition. The most common is you're trying to show that inertia, holding things in order in the fluid, compared to, viscous forces holding things in order in the fluid compared to inertia, which means every little chunk of fluid's going its own way because it has a lot of inertia, right? That helps dictate when you might expect laminar flow to be changed to turbulent flow. It's a parameter that's used for that. All right. So Reynolds number, your old friend, ratio of inertial to viscous forces in the fluid. Grashof, well, we use the Grashof up here for natural convection, and there it is, G beta delta T L cubed over nu squared. It's a measure of the buoyancy of the viscous forces. How things, want to be moved because they're buoyant versus held steady by viscous forces. So this is the general template for a lot of convection heat transfer. You're looking for correlations, and these correlations are built around dimensionless groups of terms. Well, when you need to evaluate properties, you have to be very cautious because you have to evaluate the properties at the right temperature, because properties often are temperature dependent. So here's a couple concepts. One is often you need to use a film temperature to evaluate the property. What is the film temperature? It's the surface temperature plus the fluid temperature far away from the surface divided by 2. It's an easy average. There's also, you may see in correlations, correction factors that look like this or look like that. What are they trying to do? They're trying to account for temperature-dependent properties, because one problem may have a great delta T and another problem a small delta T, or one problem may have much more temperature-dependent fluids than others for properties. Well, what are this? This is a Prandtl over Prandtl, but Prandtl number M, Prandtl number S. The S is for the surface temperature. M is the mean fluid temperature. Well, is that the same as the film temperature? Not really. And so we're going to talk about that mean temperature some more. But it's raised to a power. So you may see this tucked in a correlation, and you'll say, oh, the Nusselt number is equal to blah, 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 blah. And then right here, this Prandtl M over Prandtl S all to a power something, 0.2 or 1.5 or something. Or they could just put the mu's. What are the mu's? Viscosity. Viscosity evaluated at the fluid mean temperature divided by the surface temperature. The viscosity evaluated at the surface temperature raised to a power. So what about this mean temperature? Well, the average of the mean temperatures is the mean temperature maybe on the inlet and the mean temperature on the outlet. So if you just see T sub m, sometimes T sub m with a bar on it, sometimes not. It just means evaluate at the mean temperature, which means typically I have internal flow and I'm coming in over here and going out over there, and I could talk about the mean inlet temperature and I could talk about the mean outlet temperature. And so the mean temperature, sometimes they'll drop that. They really probably should say the average mean temperature is the average between the inlet and the outlet mean temperatures. Is this getting confusing? But before we talk about the mean temp, talk about the mean velocity. I have a tube right here, and I have fluid flow down the tube. This is the center line of the tube where the radius is 0. And so I'm thinking about the velocity profile as being a function of radius. What does the velocity profile look like? If it's laminar flow, it's parabolic. Most time it's turbulent flow in engineering applications. If it's turbulent flow, it's not parabolic, it's more U-shaped or bullet-shaped or plugged shape. So if it's shaped either like this, that's indication of laminar flow. If it's shaped like this, where it's fairly uniform over the core and then there's some steep changes at the edges, right? More like plug flow or something like that. We know that U is a function of R. The velocity is slow at the wall, actually goes to no slip boundary conditions, so it's at 0 speed at the wall, and then it's fast in the core. It depends on turbulence and what the Reynolds number is, what's the profile. But we'd like to have a very simple equation for the mass flow rate. What would be the simple equation for the mass flow rate? The mass density, cross-sectional area, times what? Some appropriate m velocity. A lot of times we leave off the subscript m, but what would that m be a subscript for? The mean velocity. A lot of times we leave the subscript off. We just say rho UA. But we're really saying that that U is a mean velocity. Somebody says, I know, but if I needed to calculate m dot, I could do it by integration. What I would do is I would look and I would do every little ring, starting from the inner ring to the outer ring, and I'd integrate over that area. So I would sum up over all of the little cross-sectional areas, thinking about doing it in rings, where I'd have the density at that ring, the speed at that ring, and I'm just emphasizing U is a function of R, not U times R. It's a function of R times dA. Would that work? Wouldn't that give me? And so this is the way you get the definition for the mean speed. Typically, these are the same. If in general, if you really wanted to carry calculations for density as a function of location, you could do it, but very, very rarely do we do it. But you get the equation for the mean velocity is 1 over the cross-sectional area, the integral of U as a function of R, dA cross-section. Somebody says, I want you to flush out this integral. Okay, then I'm going to have to replace that by 2 pi r dr. Isn't that little dA? And then I'm going to integrate. Lowercase r goes from 0 to cap r, the radius. Okay, great. Let's now that we did the review of that, let's talk about the mean temperature. So we think about our pipe, and we think, okay, we had a velocity profile. Do I have a temperature profile possibly in this pipe? Well, if the pipe is being used to transfer heat into the fluid or take heat out of the fluid that's flowing down the length of the pipe, you bet there's a temperature profile. And so the temperature profile could look like something like this. Something like that. What would that say about the temperature at the wall? Here I'm showing this is the direction of increasing temperature. Is the wall hot or the wall cold as I sketched it? It's a hot wall, right? Somebody could also say, no, the temperature profile is more like this. I'm going to show temperature in that direction. What are they showing you there? The wall's cold. The wall's cold. So the fluid is a hot fluid. There's transfer heat to the wall if the wall's cold, right? So either way, it doesn't matter which one you do, they're work out. But what we want is we would like a simple equation for the rate of energy flowing down. Just like we had a simple equation for the mass flow rate down the tube, we'd like to use a simple one for that. And so we would say, well, wouldn't that be the mass flow rate times the specific heat constant pressure times that temperature? That mean temperature? How would I go and calculate it if I was going to integrate over the cross-sectional area? Well, it would be like integrate over a sub c of what? Rho u, that gives me that m dot, right? Rho u dA gives me the m dot. Then I have the specific heat constant pressure and the temperature. And that temperature, let me try and change color here, is a function of R, as well as U, I didn't leave enough room, is also a function of R. So it's not necessarily a trivial integral if I have a complicated velocity profile and a complicated temperature profile. But the concept to an engineer like myself and yourself is easy, right? All right. So the equation would be, I would take and replace this m dot. I would say that's equal to rho u mean cross-sectional area, the c sub p, t mean equal to the rho u is a function of r, c sub p, t is a function of r, dA sub c. Typically the density we don't care about. World's complicated enough without the density and the specific heat varying in the cross-section of the pipe. So we get that the mean temperature is equal to 1 over u mean A cross-section integral of u t dA cross-section. That's our mean temperature. What are you trying to do with this mean temperature? Sometimes they'll call it the mixing cup temperature. That is very appealing to me because if I take the pipe and somehow I magically divert all of the flow for a little bit into a well-insulated mixing cup, and I then measure the temperature of the water in that well-insulated mixing cup. I'm not losing any heat or gaining any heat to the surroundings. All I did was, for a second, I took all the flow that was flowing down there and put it into a mixing cup. That would give me the mean temperature. That would be precisely the mean temperature of the flowing fluid. Why do we make such a point of this? Well, properties of fluids are temperature dependent. Correlations say I need to know the viscosity. It's temperature dependent. The Prandtl number could be very temperature dependent. Well, I have to know how the correlations were packaged and how they want to be accurate. To unravel them, I need to use the appropriate right temperature to evaluate those fluid properties. So when we see this Tm on the inlet, we know what we're talking about. It's the inlet mean temperature, as if I had a mixing cup on the inlet. The mean temperature on the outlet, that's as if I had a mixing cup on the outlet. And this is the average mean temperature used in many, many correlations as the appropriate way, the temperature, and then evaluate properties at that average mean temperature. We have studied external flow a lot. Fluid mechanics, boundary layer, the development, everything. Heat transfer, the same thing. Let me do it here for 15 minutes. You time me. And then if I go over 15, you say, please stop. All right? Well, here we go. We have flow over a knife-edged flat plate. A lot of people don't put in the knife-edged. I like to put in the knife-edged. Why? Because if I have a blunt-edged flat plate, the fluid packet here's got to go that way, and it throws it up over, and then I get recirculation, everything else. I put a knife-edged, it cuts it perfectly. All right. Razor thin, knife edge, flat plate. So I don't have any bump up and trying to get it to separate. It starts to just come in perfect that way. You have a laminar boundary layer develop. It grows. The thickness of that boundary layer is a function of the distance down from the leading edge. What is the thickness of the boundary layer, the velocity boundary layer, or what you might call the momentum boundary layer? How do we define it? Well, we say that's where the velocity goes from no slip 0 up to 99% of the free stream velocity, u infinity. So it's kind of a funny way to define it, but you think about moving in the direction y out. So you find that u, as I move y until it comes to the thickness of the boundary layer, is equal to 0.99 times u infinity, 99%. When I teach fluids and heat transfer, I always say, why didn't they pick 95%? Why didn't they pick 98%? This book uses 99. Do you think other books in engineering might use 98 or 99.9 or 95%? And I am so glad that we're not tortured with, open one book and it's 97%, open another book and it's 93%, and open another book, it's pretty uniform, it's 99%. All right. If you go far enough down, you can see a transition from laminar flow to turbulent flow, where the majority of the boundary layer, the flow is not, you have to think about a time average velocity at a point, which still is down the surface of the plate, but it could be backflowing at an instant. You could have recirculation. You have turbulence. All right. When you have turbulence, the boundary layer typically grows a little faster, but what happens is there's still a thin laminar sublayer or viscous sublayer, which really controls the removal of heat from the surface. So if you wanted to move heat through, you've got to get it through a viscous sublayer. So the turbulence, once you get it out into the turbulent boundary layer, it's whisked away pretty easily, but getting it out there is the challenge. So now it's a lot easier to get it out there instead of a big, thick, all laminar boundary layer. So the convection coefficient goes down when you get turbulence. To promote heat transfer off of a surface, rip up the boundary layer, rip up the laminar part, rip up that laminar sublayer part of the boundary layer. And you'll see a lot of strategies to augment heat transfer by tripping the boundary layer, making it turbulent earlier than maybe what it should be, or making it even more turbulent. This is the restriction right there. Well, we have the Reynolds number defined as rho u infinity distance x from the leading edge divided by mu. So as x grows, the Reynolds number grows, and that really helps us predict when you get that transition. What is the critical or the transition Reynolds number for a flow over flat plate? One of those numbers that you have memorized. 500,000. 500,000. Flow inside a tube, 2,300. 500,000 for flow over a flat plate. Well, we can calculate two things of interest. We could calculate tau sub s when we're thinking about viscous shear forces acting on the plate. What is tau? And what is the subscript s for? Shear stress at the surface. And then, if you wanted to, you could cast that in dimensionless form, C sub f. That would be the shear stress at the surface, and I want to normalize it. Well, I got to normalize it by something that had the same units as stress. And you normalize it by, anybody want to throw that out? Yep. 1/2 rho u infinity squared. What is 1/2 rho u infinity squared? Name for it. It's like a force per unit area, but it's a normal force per unit area, not a shear force per unit area. And so it's as if I brought the flow to rest right there. That would be a pressure increase. That would be the velocity pressure or the dynamic pressure. So, but it has the same units as a stress, force per unit area. It's not shearing though, it's normal. All right. So we get correlations for this C sub f. Oh, did I emphasize, what is that skin friction coefficient? Is it dimensional or dimensionless? Dimensionless, dimensionless. So we get a correlation for it for both the laminar, and then we get some experimental curve fit, and we get the correlation for predicting the shear stress for a turbulent flow. Then we talk about the local as well as the average over an area. Well, same thing, you have the thermal boundary layer. The thermal boundary layer can grow as fast as the velocity or momentum boundary layer when the Prandtl number is about 1. Right? And then it can grow a lot lower or slower than the velocity if the Prandtl number is what? Less than 1. And then if it's high, well, I'm sorry. If it's high, it'll grow less than 1. If it's low, it'll grow faster than 1. Okay, the average Nusselt number, Nusselt, you can talk about it as a location x, dimensionless ratio of measurement of convection coefficient. And then you could talk about the average Nusselt number. Well, just for flow over a knife edge flat plate, Reynolds number, skin friction coefficient, local, Nusselt number, local, the average skin friction coefficient, the average shear stress, the average Nusselt number, the average convection coefficient, and we haven't even gotten to turbulent. But the pattern is they're all bundled up in the dimensionless coefficients and in correlations. Here's a pile of them, and I truncated the list. It seemed like the same table was in both books, but I got it out of the heat transfer text. What happens if I'm looking for flow inside of a tube? Well, if I have flow inside of a tube, I can have the same thing like flow over a plate. I could have laminar flow, or I could have turbulent flow. The critical or transitional Reynolds number for flow inside a tube based on the diameter of the tube is 2,300. And now you have the friction factor is a 64 over Reynolds number, or I have two Nusselt numbers depending on the boundary condition, uniform heat flux boundary condition or uniform temperature boundary condition. these aren't encountered as much in practice as as much as you see of them in the heat transfer textbook. A lot of cases are turbulent flow in practice inside of tubes. You still have some that are laminar, but a lot of them are turbulent. So anyway, you keep looking, and then you find, oh, here's the friction factor correlation for turbulent fully developed, and the list goes on and on. Here are the three that you really should become familiar with. So for flow in a smooth circular tube, what do you mean by smooth? Not a lot of roughness. It's turbulent flow. It's fully developed. How long does it have to take before the flow comes into a tube before it becomes fully developed? How long, how far down do I have to go before it's fully developed? If it's turbulent flow, you should just remember this one. It's a pretty easy one. That length to become fully developed is around 10 diameters. If it's laminar, it can be longer. Okay? So turbulent flow, about 10 diameters. Okay. So let's say this correlation right here. Maybe you've seen it before. The Nusselt number is a function of diameter is equal to 0.023 Reynolds to the 4/5, Prandtl to an exponent n. This is the Dietz-Bolter. We use a lot because of time-limited examination in heat transfer class. But it's not the most accurate. Sider-Tate. It's a little longer because here I've got mu viscosity, then I have mu sub s, the viscosity, so I evaluate the viscosity at the mean temperature and evaluate the viscosity at the surface temperature, and then I have that additional correction to help it to be accurate for temperature-dependent properties, as well as have the same type of Reynolds and Prandtl, but this Prandtl's to the 1/3, and then a slightly different coefficient. So Sider-Tate is about as easy to use. There's a couple other ones. Petukov, I didn't copy it out, it's in our textbook. This is, Gronelski, I don't know how to pronounce his name, but anyway, you can see they're getting more complicated, but they're reported to be more accurate. But what is this? F/8, what is that F? The friction factor. You would need the Moody diagram or some equation like the Churchill equation to be able to get it. The Reynolds number minus 1,000, Prandtl number, Prandtl to the 2/3, etc. It's a curve fit. And whenever you have these equations, you always take a look at the footnotes in evaluating properties at the average mean temperature from inlet to outlet, as well as making sure that the Prandtl number of your fluid is within the range of the correlation. And if it's being heated, use 0.4. If it's being cooled, use 0.3. All right, there's lots of things to double check. Correlations for fully developed flow in rough circular tube. Here it's not smooth. What do? Well, use this correlation with F based on getting it as a function of relative roughness as well as the Reynolds number. But what about Dietz-Bolter? How could I take into account the roughness of the tube? You can't. There's no way to take into account the roughness of the tube with either the Sider-Tate or the Dietz-Bolter correlation. Laminar flow inside of channels, you get the Nusselt number for the round 4.36 or 3.66 depending on the boundary condition. But if you have a square channel, rectangular with the ratio of A/B to B2 or the ratio to B4, you get different correlations, different numbers for the fully developed laminar flow with those boundary conditions. Let's solve a problem. So we have counter flow concentric tube heat exchanger. The length is 20 foot, and I'll just try to sketch it like this. So we have some hot fluid, we have some cold fluid. All right, and so the length is 20 foot long. It's made of 2-inch copper tube, and so think of copper tube, you have an ID for the flow inside. So the ID is 1.760 inches, and the nominal wall thickness T of 0.120 inches. What's the OD? Can you calculate the OD for me? Of this copper. You have a thickness on that side and a thickness on that side. 2.000 inches. All right. It's copper tube. You can look up the thermal conductivity of copper. Water enters at 60 degrees F with a velocity of 6 foot per second inside the inner tube. So this one is the water on the inside, and its velocity is 6 foot per second. On the outside, you have steam, and it's condensing, and its temperature on the steam is 220 degrees F. The water temperature of the, here I'll put it over here, temperature of the cold inlet is equal to 60 degrees F. And when the steam is condensing, it comes in, hot in is 220. It condenses, the steam leaves at a saturated liquid of 220. So the temperature, that's equal to the temperature hot out. 220 in, 220 out. It's just condensing at constant pressure. And they give us the H on the outside. The H on the outside is 2,500 BTU per foot squared hour degree F. Determine the outlet temperature of the water. This doesn't seem like that hard of a problem, right? The temperature of the cold on the outlet, that's all we're asked to solve for. Well, what you're going to have to do is you're going to have to calculate the overall heat transfer coefficient U, and use then the effectiveness NTU method to calculate the outlet temperature of the water. All right, so let me outline or highlight what you're going to do here. Is you're going to try to find 1 over U, and I'm going to base it on the inner area. And that's going to come from 1 over the convection coefficient on the inside area inside of the wall pipe, plus the resistance through the copper thin-walled tube. Well, I'm going to do it as the natural log of R outer over R inner divided by 2 pi KL, and then we have 1 over H outer area outer. Okay. The area in is pi d in L. Is that true? Okay. So what you can do is you can rewrite this as 1 over U in is equal to 1 over H in plus natural log of R2 over R1 divided by, you're going to put pi, you're going to put D over 2, thermal conductivity, that's it. Did I do that one right? Plus 1 over H outer D inner divided by D outer. That makes sense? All right, so I start checking. I say that was given. The diameters are doable. The radius are doable. The diameter is doable. Thermal conductivity of copper I can look up. I'm stuck right here. How do I get H on the inside? You have to do a lot of work to get H on the inside. So I come up here and I say, how do I do that? Well, H on the inside is going to be the Nusselt number based on the diameter on the inside times K over D on the inside. So I need to get the Nusselt number. I have forced convection through the tube. Which correlation do we want to use? You can use the Dietz-Bolter, you can use the Sider-Tate, you can use the other one. The most accurate is this one right here. So let's do this. I need the Reynolds number, and let me stay on this page for a minute. So I need the Reynolds number. All right, that's density V diameter divided by mu. So I need the fluid properties, and the problem gave me the speed in the tube, 6 foot per second. So you can calculate that Reynolds number. When you calculate the Reynolds number for this problem, let me see if I have it here. I know I have it, I just have to find it. Okay, 72, 131. Turbulent? Turbulent. So this is the right correlation to use. If it was laminar, then we'd have to go look for other correlation. And then we get the friction factor. It's smooth. At that Reynolds number, you can go to the Moody chart, 0.0192, or use the Churchill equation. Now that I have the friction factor, the Reynolds number, I need to get the fluid properties. I already had to get the fluid properties. I had to get rho, mu. I have to get Prandtl number, thermal conductivity, all of the water. But I get the Prandtl number of the water. This is where, in the problem, you say, I don't know the outlet temperature of the water, but I'm needing to get the temperature, average temperature of the water, mean temperature of the water to get the right fluid properties. So you have to guess. That's all you have to do, and you have to iterate. In a code, it's not that hard. By hand, it gets tedious. So I think I used 60 degrees. So I said 60 degrees F, thinking that it's going to be coming out. What did I use? Yeah, 60 degrees F or 70 degrees F. Actually, I used 70. If I use that to evaluate the water properties, that's 10 higher than the inlet. What is the inlet temperature? 60 degrees, right? And hence, it's the outlet should be, I'm guessing, is around 80. That's how you think about it. What do I think the outlet temperature is going to be? All right. So I get the properties. I then go back to my correlation. The Prandtl number is more, and the viscosity or temperature is sensitive. These aren't as dramatically temperature sensitive. But we calculate the Nusselt number, and the Nusselt number is 501.7. That's using this correlation right here. What happens if I'd used the Dietz-Bolter? The Nusselt number, Dietz-Bolter, comes in at 427. It's a big difference, isn't it? But that's just the nature of convection. You have to use your best correlation. And the better correlation in the literature is that one.
Which one are we more likely to use, sir?
I would use the one that's reported to be the most accurate when you're doing it in Excel. And when you're doing it on an exam, usually I tell students when to use. And I've told them, just use the Dietz-Bolter or Sider-Tate and never use that other one. It's too error prone on a timed exam, 50-minute exam or something. But that's only for examination purposes. Okay, so what we do then is we go and we get the overall heat transfer coefficient based on the inside. The overall heat transfer coefficient is, I'm looking for it. Oh, I'm sorry. The convection coefficient on the inside is 1187 BTUs per hour foot squared degree F. So this one is 2,500, but you really do have a pretty good convection coefficient on the inside, don't you? The fluid is really whipping through the system. When I compared the resistance due to convection on the inside is around 68% of the overall resistance. The conduction through the wall is around 3% of the resistance, and the convection resistance on the outside due to the condensation is around 28% due to the resistance. contributing to the resistance. Okay, so we get an overall heat transfer coefficient, U, based on the inner area is about 809 BTUs per hour foot squared degree F. Now I can calculate finally the number of transfer units. UA, both of those need to be on the inside, divided by the minimum heat capacity rate. The minimum heat capacity rate's for the water. The water has the minimum heat capacity rate. The steam, remember, C infinity, C max, because it's condensing, undergoing a phase change. For this problem, it comes in at 0.3285. What are the units on that one? Dimensionless. We then take a look and use the simple equation. Maybe it was way back here. This one. Because once fluid is condensing, undergoing phase change. So we say, what is the effectiveness? The effectiveness then comes in at 28%. Then I calculate Q maximum, assuming C min times T hot in minus T cold in. And that one was a lot. I mean, it's 1071 BTUs per second. To calculate the actual Q, around 300 BTUs per second. Hence, I can get finally the temperature to the cold out, which is the actual amount of heat transfer between the two fluids in this heat exchanger, plus I usually put the temperature cold in, plus Q divided by the heat capacity rate of the cold fluid. Then the temperature cold out comes in at 97.6 degrees F. So if just tuck up here, so it's 97, 98 out. It came in at 60. So 60 plus 98 divided by 2, the average temperature should be about 74. If I wanted to, I would go back and say, what did I use for the temperature to evaluate my fluid properties? And you now update it and redo the whole calculation with the average mean temperature for the water to be 74. You only have to do that once. It was pretty close anyway. All right, did that help? So yes, part of this class is doing exactly like this, going back and reviewing the heat transfer and slugging through those calcs. Did anybody have a comment or question? Thank you very much for your attention. We'll see you next time.